Because I've had lectures where all I had was, without that, you get no noise. So, what do you think of this paper? Was it easy to read? Was it? So this is more modern version of SOSP than the first papers we saw. You can see that they begin to follow this sort of SOSP pattern, right? SOSP pattern is you kind of cram like 9-point font, single-spaced. That's what ACM format is. Single-spaced stuff into 14 or 15 pages worth of, I don't know what the page count is, into the stuff, right? So there's lots of stuff, right? If you try to read the stuff, most of your conferences, especially in other areas, you get like 4 or 5 pages kind of thing. But this one is like you can write whatever you want kind of stuff. So they add a lot of stuff. They thought through a lot of the stuff, right? And one of the things I encourage was people should be skeptical of what they're saying. But on the other hand, I don't want you to be cynical, right? I want you to be skeptical of how it relates to where we are, but you have to give them the credit for whatever, right? So for whatever the reason is, they got their paper accepted to the top conference in the field, and this is a single author paper, the student author paper, right? Dawson was the student author on this paper, and using that he went to Stanford as a faculty. So some people thought this was excellent work, right? So try to find out not just the critiques, but also opportunities, right? Not that I'm saying that every paper you'll find opportunities, but keep that in balance. Like, it's not all about trashing the work, because there's some important concepts, right? And the important concepts here is, in your undergrad OS, you probably were never taught that how to organize the operating system itself is a pretty hotly debated topic. What is the role? What does operating system do? Where does it fit? And all those things were probably sort of left undefined, right? Because you kind of told that there's a hardware, right? We don't bother with how the hardware is set up, whether it's a firmware based, or for folks who are in hardware can tell you that that's not really the case. I mean, it's not a trivial case, but we assume that there's some kind of hardware, and we assume that there's some kind of application, and then we kind of assume that there is something we have to do in the middle, and then you kind of talk about processors and threads and all those things without trying to figure out where this whole thing fits, right? So there's 3 schools of thought, and you might have heard the first 2 is the notion of monolithic kernel and the notion of microkernel. And this one takes it to the extreme, take the microkernel to the extreme, where you not only take the policies out of the kernel, but you also take the mechanisms out of the kernel. And on one of the reviews I saw, the first one, they claimed that the mechanisms were left in the kernel. No, the mechanisms, as far as possible, they wanted to be out of the kernel, because mechanisms do imply some sort of a policy, right? So if you talk about pages, and if you want to talk about in page numbers and stuff, the more you abstract, the more you have some sort of mechanism, however small it is, you're not giving power to the application. So the kernel should be as small as possible, do practically nothing, and export as much of the mechanisms as possible. And the rest of the paper is about dancing or trying to figure out how far you can be doctrinate about it, and how much you can get away with it, right? And as you can see, that it's not the easy task. I mean, when you want to take that role and you say the OS should do nothing and everything should be moved to the application level and you get good performance, right? It's a good argument in some perspective, but then you have to look at the whole picture. So what is the whole picture of the whole? So I think I have a slide on that in a little bit. So what is the point of having an operating system? What is the role of operating system applications and all those things in the grand scheme of things? Anyone want to comment? Yeah.
That to abstract away the lower level workings of the machine from the programmer, so that you don't have to know everything about how the machine works in order to use it.
Yeah, we'll go with that definition for a while, and I'll have it. Yes. Hey.
The OS should manage the resources, and the configs should be resoluted by the OS.
Okay. So let's stay with that for now, and I'll come back to that and argue that it's not as simple, because the issue here is who is they and who is us, right? So there is this OS developer, and there is this users, and there is this hardware people, right? So there are 3 kind of people up there, and it's easy to say OS should provide all the stuff, right? And we as users should benefit from it, right? but they're not like Martians or something, right? So they are also developers and all those things. So you can't completely abstract away their concept, right? So you kind of all these things is basically going back and forth between who's OS developer and who is not, right? And you will realize that in a lot of scenarios, OS developer is not somebody who's sort of behind a glass box or something. They have to work collaboratively with you, and I'll show examples of why if you don't do that, you get bad performance, and that's where all these things come up with, right? If you want to write a hello world program, what you said is absolutely true, right? I don't want to be bothered with terminals and screens and what have you. I just want to write in a small high-level programming language, abstract everything away. I just want to say hello world on the screen, and I just move on. But that's not all that we do, right? So the idea here is to make everything into libraries, right? So if you think of the microkernel world, right? Essentially, most of the mechanisms and all the policies, you move them out of the kernel, right? Rather than run as application servers, which is how microkernels did, you link them as a library into your application, right? But I think that's not that big thing. But essentially, what you want to do is you want most of the stuff out of the kernel. The kernel is very small. That's only 3 things, and then you move all that stuff to the libraries, right? And these libraries, anybody should be able to write it. These libraries are not designed to be portable, right? Because they have to manage all the things that you traditionally assume the operating system to be doing are maintained by these libraries, right? So they have to know what the page size is, they have to know what the instruction is, they have to know what TLB is, and all those things. The less they know, the more they look like microkernel, right? The more they know, the more they look like exokernel, right? If your libraries know everything about the hardware, right? Practically everything about the hardware, every interrupt and everything, then they look more like microkernel. Then the library also looks like it's like an operating system, right? So that's the tension that they're trying to face, and so we again going back to what we had in last lecture. Have all these abstractions. What is the problem that they're trying to solve, right? I think the problem they're trying to solve depends on so what is the problem they're trying to solve? Why did this notion come at all into picture? I think they started in the first sentence here.
So is it how to give application programmers the knowledge and power to do what they want?
Mm-hmm. Yes, they want the applications to have absolute power, right? Interface, everything, whatever it is about the machine, they should know, right? So let's look to see what kind of application would want that kind of a control, right? And again, like we kind of mentioned, traditionally the operating systems, you want them to be abstracted. So your undergrad operating system class probably started off with operating systems abstracts away all the details and then gives you this unified view, and you can write portable code, yada yada yada, and all those things, right? So this is sort of what we kind of pound into the undergrad class. Don't worry about it. Operating system will solve that for you. It gives you a good abstraction. It gives abstraction of a thread, but it doesn't bother to tell you that you have 2 processors or you have 10 processors. And for the most part, don't have to worry about it. You just write code, and if it's on 1 processor, it'll work, and 10 processors, it'll work, blah, blah, right? But there are a lot of cases where that's not exactly true, right? So depending on different fields, I don't know what field you are in, right? So one of the classical examples is databases, right? How many of you have experience with working with or writing or thinking about database? How many of you taken database class? Right? A few of you, right? So it's like half of the class, right? So in the databases, one of the things you want to know is you want to have consistency. You want to have data consistency, which is one of the main aspects of database, right? You don't want to have a best effort writing. So if I write a transaction, if it's committed, I want it to be on stable storage, right? Which means that I want it to be flushed all the way into disk. I don't want any kind of buffering. I don't want any kind of optimization. I want to have absolute control over, if I say this has to go in the disk, it has to go in the disk. It has to be written into the disk, and I don't want to come back till it's done, right? I don't want to, unless I'm forced to, I don't want to deal with blocks and stuff, because I know how I'm maintaining my data structure, right? Because I have, let's say, index database. So I know what the fields are in my stuff. I know how they're indexed, and I want how they should be organized and all those things. So I, as a database developer, know more than you as an OS developer, because I know what I want to do, right? And I know what the hardware is, and you're getting in the way, right? One of the other reason is database is actually probably a lot more expensive than your operating system, right? So if you buy a real database, not Windows Access or something, right? I'm not belittling Access because it's not industrial strength, but mostly the scale, right? So if you buy say Oracle server, and so many of them cost a few millions of dollars, right? Just the software, right? So you want them to run some mission critical stuff. You want to, let's say you paid $10 million for Oracle database, and you bought this whole room full of servers, and you have all this stuff. You don't, at that point, you don't want to say, well, this is fine, I'm running on your favorite operating system, right? Running on Mac or Windows or Linux or whatever you can think of. And they impose these restrictions, right? They impose the file system should be formatted as ext2, whatever you can think of. So I have to do it on that, the way they want it, right? You don't want to be restricted like that because, hey, the machine was bought for databases. So I have no interest in making it general purpose. And the real customer does not care either, right? So if you're selling it to Notre Dame does not say, I want an Oracle which runs on vanilla your operating system. They want this database to do what they want to do. So they want absolute control. So if you take database course, one of the things they constantly worry about, harp about is, how do I do what I have to do while still working with a regular operating system? And you'll notice that that's not a trivial task. You have to go through hoops to make sure that these things happen. And so those community would say, the best operating system for us is you get out of the way, give us the control, and I do that, right? The other cases, simple cases, movie players, right? How many of you used movie players on your computers, like playing DVD or something like that, right? So what's one problem with those kind of things? Have you faced any problem with using those things? Are you happy with the way it works? Yeah.
On some older machines, the I/O bandwidth and scheduling was not always adequate too.
Yeah, it kind of, if you had a fantastically resource-rich machine with lots of memory and all those things, you may not notice it. But for most normal machines, things stutter and things happen when you don't want them to happen. And because you're using all the stuff with the system, you want to have full control over the system. You want to get rid of all the stuff because you know that this user is only watching a movie at this time. They're running in full screen mode. So you would like to say, give me full control, I take care of it. And if I don't have anything, I'll give control back to other stuff, right? So you want these things to take control over the stuff. The last one is games. How many of you play PC games? So what is the best operating system for writing a PC game? Windows Vista or DOS? I don't know how many of you know DOS, but there used to be an operating system called DOS, right? DOS, right? Why?
It's single thread, isn't it? Or in order to give control, so if DOS gives control to an application, the application has to explicitly give control back to DOS before DOS can do anything else.
DOS, okay. That's a good way to put it. But the real way is DOS is not an operating system, right? It's very easy to get rid of it, right? So basically, most of these things, they get rid of it, right? So when they're done, when the game is done, they give control back to DOS by essentially starting DOS, right? So DOS is a beautiful system because the beauty of DOS is you can get rid of it, right? You can completely get rid of it. It does not do any of the things that you learn from operating system. It does not do protection. It gives some abstractions, but the best abstraction it gives is you can get rid of the whole thing, right? So in that sense, I think DOS is better than Exokernel, right? Because Exokernel at least controls something. So if you have two competing stuff, Exokernel are to prevent two library OSs from stamping on each other. DOS doesn't even do that. All of it is in view. And if you think about that past, it was great for doing something like games. You had full control, the games was completely playing. It was great for everything else too. Virus programs were very easy to write because they can just get rid of everything, right? So all these people want this kind of control because they know that if you're buying a PC game, they know that gamers are buying these machines for running games. So they would like absolute control over this stuff. They don't want all these abstractions because they want absolute performance. They want absolute speeds as much as possible. And they're always clamoring for ways to get rid of all the operating system, right? So one way you do that is you work with the OS companies, right? So if you if Oracle does not wait for the Windows Vista to come out on the market and then try to port the operating system to it. They work extremely closely with these developers, and you come up with a version of OS which is, they call it like Windows Vista Oracle or something, right? It's tuned to do certain things as well as possible. So that machine is not really designed to be a general purpose operating system. It looks like Windows, but it's not really Windows, right? So depending on the market, this sort of thing goes on all the time, right? So there's real need for these kind of systems because abstractions are good. Like abstractions are good, but some places abstractions are not good, right? So what kind of applications or what kind of users want full control and what kind of users don't want full control? You think? That's important because when we talk about all this stuff, these others kind of go back and forth and mix these two users, right? When do you want, you as a user, when do you want full control over what the OS does and when do you don't care about what the OS does?
When you want performance, you want to be able to say exactly what the OS does and when it's allowed to do whatever it's allowed to do. But when you're doing just standard, maybe text editing, it's kind of okay that it's a little bit slow or stuff doesn't get exactly flushed out to disk. Well, that might be a little bit more of a concern, but I mean, I guess it's when you're doing really performance-oriented things.
I think that's an excellent point, right? And many of you kind of ask the question why. I mean, they start off by complaining that all the prior abstractions that people have said in SOSPs, and we'll read many of those papers in the due course, right? They talked about all this stuff, and none of them are in commercial operating systems. And we're going to propose this exokernel mechanisms, which will mean that any research project you come up with will be available to the user kind of stuff, right? And many of you pointed out that this was written in 95, 94, some time frame they did this work, and this is 2008, and I don't see this happening in commercial operating systems, right? And I think the bottom line is this, right? There seems to be two kinds of users, right? The casual users who don't practically want to get the last bit of performance out of the system, and then these people who want everything out of the system, right? And since it's not clear that, I think each of the approaches have good stuff, and you see cross pollution between all the stuff. So I don't believe that the exokernel ideas were completely thrown off. It just gets added slowly into the general theme of things, right? Some of the stuff, so if you're writing a hello world program, you don't care about all the stuff. But if you're writing the games, you want control. So it's not, I mean, it kind of goes back and forth. So maybe you don't see Windows Vista advertising that we use exokernel, but all the ideas kind of percolate into these things, and that's one of the reasons why we want to read the stuff, right? And you will also run into this problem when you try to do something important, regardless of, like, in your research area, if you're trying to do some things, right, and if you want to do something beyond the simple hello world kind of stuff, you always run into stuff where you want to do something, the hardware can do, but you just can't do it because there's all this stuff that you have to go through, and you lose performance because of those, right? And part of the reasons why you take operating system class, why it's a core course, is you have to know what is happening and try to write your code differently, right? And that's why I think that all of you have to be here, because whatever you do, you cannot say, I want to run this code and I want to run it faster, but it's not running fast and I just give up, right? You have to try to figure out why it's happening, right? But this is going beyond that. It's saying, okay, you don't have to even settle for that. You can sit down and write the operating system that'll make your project go really fast, right? So for people who are doing, like, say, data mining of large objects, you can write the operating system which does data mining extremely well, right? Just you write your own libraries and own stuff. It works fantastic for you. People who are doing grid computing, your system will be an excellent grid engine, nothing else kind of stuff, right? And so that's their logic, and let's see whether you agree with it and whether you're going to start using exokernel for your projects. One of the other comments I noticed was people are complaining that there hasn't been much work done since then in exokernel, right? So one of the realities of which I think the first papers talked about is student projects are, when you leave, so you do some earth-shattering technology, right? So when you leave academia, when you leave here, get a PhD and move off, projects tend to die, right? Because you get a new job and you kind of move on. And that's not an indication of how good or bad the project is, right? And that's the reality of the academic research. It's sort of like what Dexter was complaining about, right? So it'll happen to your own career too. Before you get a PhD, you'll do a lot of interesting stuff. You come up with some interesting ideas and you publish and stuff. But many of you may not continue with it forever in your life. I mean, you move on to different stuff. You come up with different ideas and stuff. But just because you move on doesn't mean that it's a bad idea, right? It's sort of a defense of these things. But we all will do that because we all move through different phases in life, right? So that's not an indication that this is not a good idea. So what does in Exokernel, it only provides 3 abstractions, right? One is the notion of a secure binding of resources, and the other is the notion of a visible resource revocation and an abort protocol, right? So what is a secure binding? So I'm going to start from here. So what is a secure binding in your view?
They want to link a resource to an application or a library or something so that they can, I don't know, I just kind of think of it as like a session, like you have access to that thing when the OS allows you to have access to it. I could, of course.
So some way that Exokernel can give you access to a certain resource, right? So why is it called secure and not resource allocation?
The applications can't do it without the approval of the Exokernel.
Okay, so is that true?
Well,
Do you want Exokernel to?
You can't really, I mean, you can't access another application's binding. You can't access.
So how do you want this to be enforced? Yeah, so I think that's the right thing, right? So you want Exokernel still wants to control resource allocation, right? It does not want to let you do whatever you want, like in DOS or something. So it wants to have control. So it can give these resources to you, right? So what happens then?
After it's assigned, or
Yeah.
so the application library can then use it. If there's an issue, then it can run the abort and just cut the connection.
Okay, so I can give the resource to you, and you are allowed to access it, right? And so I have to make sure that you have access. You are using the resource that is allocated to you, right? And also make sure that you don't access resources that are not assigned to you, right? How do we do this in a traditional operating system? How do we make sure that some resource which is allocated to you is only used by you and you're not using something else, right? The safety argument from traditional operating system, right? How do we do that in traditional operating systems?
Like exclusive block on the resource.
That's one way, right? Let's look at file system, right? File system, how do I make sure that you only write the blocks that are assigned to your file and not somebody else's file? How does the operating system ensure that?
So you give the write capability to that user, and for all others you prohibit the write capability.
So I give you write capability. What then?
And until I finish, nobody can see the updated one.
So who checks the write capability?
OS.
So I give you the write capability, and every time you use it, you have to present the capability to me, right? And you want this capability to be tamper-proof, right? So obviously you don't want it to be able to change it. So I give you this capability, you can't modify it, and every time you have to use it, you have to give it to me, and I check. Is that what you think will happen?
Yes, but I mean, if there is any other request when I am writing, then the OS should, decide when to take the capability from me and give it to another.
Yeah. So the simple case, right? Simple case is I give you a capability, and every time you write, you give me the capability, and I check to make sure that you have the right capability before I let you go through, right? So I have to check that you have the right capability, and you're trying to modify what your capability says you can modify, right? Is that one of the ways you can enforce these things in traditional operating systems? I mean, it sounds like what you do, right? What's the problem with that approach? What's the trade-off with that approach? What's the best, good thing and bad thing about that approach?
Performance. whenever you want to write a file,
Mhm.
you have to check to see if you have the right to write that file.
Mhm.
It's, overhead costs.
Yeah, we have to check it. So we have to define what checking means, right? I mean, checking can be trivial or hard per operation, and how often I check it, right? And like you pointed out, if I had to do it every time you come, and every time if you come every byte or something, then the stuff can be slow, right? How do you solve that?
You can trust the user to do the writing. Don't check it at all.
So yeah, so you can trust the user will do the right thing and not check them at all, right? So there's one operation where I can check every time. Another one I can check, not check at all, and trust that you will do the right thing, right? So where does this thing fall? What is this notion of a secure resource allocation fall? Because it's the same concept, right? It's the same concept of how do you. So I gave this stuff to your application library. Do I check it every time? Does the exokernel check it every time? Does the exokernel check everything that you do every time, right? How would you do that, right? So what does the paper say how they do that? They go through a lot of sections on trying to answer that, right? Is there a general scheme that they can use for every scenario, or is it for disk we can do this, for network card we can do this, for blah we can do that kind of stuff, or can you have one concept that applies to all the kind of resources you can think of?
They had, I think he called it application-specific handlers, which is just their download code into the kernel and go to operate as part of the kernel, so it wouldn't have to go check back and forth across the user kernel layers.
They specify a couple of different things, right? They download some code and run some filters and all those things, right? But I think the underlying problem here is if you have one mechanism to do that, like what traditional operating system do, which is when you call a system call, I'm there, I check everything, and then let things go, right? Things were beautiful because there's one way, right? You only enter the operating system through the system call. You cannot address the hardware without the system call knowing stuff, right? So that means I can check every time you come. I can choose. I mean, I think the other option of not checking every time sounds dangerous, right? Because I don't want to trust applications. So I check this stuff or what have you, because for protection, right? For the most part, you check it every time, kind of thing, right? But you don't want to do that because that is a mechanism, right? The mechanism also defines that everything has to be checked in a sort of a similar fashion. They don't like that, so they have to say, give more power to the people, right? But then means different things in different scenarios. So here, if you're calling from a network card perspective, then I have to do this checking in a different fashion, right? So I have to download this notion of a filters, right? The traditional Unix and all those things have notion of filters, which essentially mean that when a network gets a packet, somebody decides that this belongs to this kernel or this kernel, and then separates it out, right? So you need to have this little piece of code which checks to see who it belongs to, and that is part of. So you are allowed to send something in to get performance, right? So that's where it kind of gets kind of murky, because if you want full power, then you have to look at each hardware and how it does stuff, and you need to do the right thing for it, right? Right? So for page table, what you want to do for the secure allocation, how you prevent the page table from accessing something else is not the same way as how you would do for a network card, right? And think of a network card. I don't know how many of you have a network background, so let's keep it at a very high level, right? So you want this stuff to be, so you want the hardware to do all it could do. You don't want the operating system to get in the way of giving you all the power you want, right? So how far can you take that, right? So for example, a card can be on 2 different IP addresses. It can be on a IPv4, IPv6, or what have you, right? If 2 different operating systems want it to be on different things, how would you do that? I mean, right now, your system would only let you be on one or the other, right? How would you take it all the way to the extreme where your hardware can do two different aspects, but they both conflict with each other if you do it? You're allowed to do one or the other. With traditional operating system, let you do one or the other or both together. How do you do that? I didn't see any argument on how I don't think you were supposed to take it that far, right? You're supposed to take it to a point where things sort of make sense, but you don't want to do that, right? Is this notion clear to you? I mean, the higher level concept is simple, right? I want to be able to give you resources. I want to make sure that you don't mess with the resources, that you don't have privilege too. But the implementation may be pretty complicated, right? So is there anything that these mechanisms do that is different from how monolithic kernel does? So for example, do you believe that if you wrote a program for, say, POSIX, right, POSIX interface, and you have Exokernel with the POSIX library, right, and you have your application on top. So here is your app, right, and the POSIX library, Exokernel, right? And here's a monolithic kernel with a iconic system calls, and here you have this kind of a structure, right? Is there any difference from your perspective between this and this? Let's not worry about the speed. Let's worry about the security and resource management issues, some of the secure resource allocation stuff. Would these things be different? How?
So the application can, modify the system call interfaces there.
Yeah.
For their own customization.
Mm-hmm.
But here you can't.
Yeah. So I'm saying we're not doing that, right? So obviously you don't have to have POSIX. You can write your own something. But I'm saying, let's assume that somebody wrote a POSIX library, right, that you're going to use, right? So your program is the same, but one of them uses the Exokernel-based system, right? What I want you to focus is who developed these things, right? So this was developed by somebody. This is developed by somebody. This is developed by somebody, right? And this is developed by somebody. This is developed by. So the same app developer is the same here. But here, hopefully, this is written by somebody. This is written by somebody, right? That's essentially what this is all about, right? So if Microsoft can do this and this all the time, then I don't see what's the point of all this exercise, right? If Microsoft is if this and this were done by the same developer and they had, all the stuff, then it's not that big a deal. Hopefully, it'll allow somebody else to write something that you can use, right? So is this system the same functionality from the application developer's perspective as this one with respect to the security of resource allocation? Can you do something differently here to hurt the system, to avoid the system, to break the system? And if you can, what kind of a breaks would you do? And is that a bad thing or a good thing? So in this, let's say in this system, right? If the system is performing properly, then essentially you have no control. As the app user, you do whatever Microsoft gives you, kind of thing, right? So in here, there's a third party here, right? The one who wrote the POSIX library, right? Can they do stuff to other? Let's say something that we did, right? We did library, right? Can they mess with something? And if they can, how do you prevent it? Does the secure allocation prevent this library from interacting with this library? Do you think it?
If they're different users, then it should.
It should?
If they're different users. If there's supposed to be different users running each library, then it should be, then the Exokernel should prevent.
Yeah, it should prevent, right? So how would it prevent?
There wouldn't be a binding to the other library, and so you wouldn't be able to use it.
No. Yeah, so this is being used by, say, another user, right? So the goal of Exokernel is to prevent whatever was assigned to this resource, this library should be used by this library to this library, right? So suppose this library wanted to access something that was assigned to here, right? How would you prevent it?
There wouldn't be a secure binding between them. If you attempted to get one and it was another user, the Exokernel would reject that request. So it wouldn't set up a binding between those two.
You think Exokernel will reject it?
We're just calling a function in the library, right? Because and it's all in user space, so the Exokernel wouldn't necessarily see it, would it? Unless you're talking about protecting the memory space. It would be part of the Exokernel job to make sure that the memory address that you're trying to access
Is that true? For memory space, does Exokernel check to make sure that what you're trying to access belongs to you?
I thought it made sure that the raw address it had some table that it said user X is allowed to access memory space.
Yeah. So who checks it?
Who checks?
Whether that, so yes, so when you have memory, right, it has to have some table which says that memory page A1 is by user 1 and memory page 2 is by user 2 and 3 is by user 2 and 4 is, let's say, free or something, right? So it has to set this table up, right? So every time you do memory access, does it check this table?
You only have binding time, right? And then once you have it bound, then you have access to it. So, something. I thought. I could be wrong.
This is an issue that yeah.
I think you do not need track if we use virtual memory here. Yeah, that's one of the part of the virtual memory is there. Probably we do not need page table. There's end users who access page table also.
Virtual memory would not necessarily solve that because they want control over the page table entries. I mean, they want each application to get no abstractions, right? You want as close to the hardware as possible, right?
The point is you want to access something outside your workspace. That's the point.
Yeah. No, they do set up this table, right, which says what the ownership is, and they give a lot of examples, right? Like I think in SGI they say on the screen the pixels can have each ownership, right? So they can say you can only access this part of the screen, and somebody else can access this part of the screen, but the hardware keeps track of who owns that pixel. So if you try to write something here when you're supposed to write here, something bad happens, right? I think I kind of said the answer in the last example, right? Who checks it?
The libraries?
Huh?
Don't the libraries check it?
No, in some of the cases the hardware does it. To get good performance, they require one of the things they mention is you want you set up this table, right? You set up this table with this neat hardware where I give you a capability that is tamper-proof, so you cannot modify it, right? I can revoke it if I want. I mean, I as Exokernel can give you a capability. I as Exokernel can revoke it by changing something, right? So the thing is no longer valid, and you give the capability. You have it somewhere, right? So it could be in a register or something where every time you want something, somebody has to do the checking, right? And that has to be done in hardware, not in software, right? Because remember, one of the easy things you can do in C or something is follow a pointer to something, right? And since I want to let you give as much control as possible, virtual memory alone won't be able to protect you because they reject the notion that virtual memory is all you can get access to. I want to get access to all the stuff there is. I want to know the stuff they go through in terms of naming, right? They don't want to know an abstracted name. Virtual memory is abstracted name, right? So virtual memory says I want the address from 0 to 1000, that's abstracted name. They want the unabstracted name, which they wanted the name of the page which belongs to the system, which in other words is called physical address, right? So they want everybody to have control over the physical address. So, which means that if I give you all that power, then you can do whatever you want, right? And you cannot expect the exokernel to be policing everything that you can do, because you have the whole machine, you know all the addresses, you know all the TLBs and all those things. So just like in traditional operating system, even in traditional operating system, this is what happens, right? You set the page, remember the page table, you set the page table, you set the bounds and everything. I let you do whatever you want inside your space, you go out of the space. It's not the operating system job which makes that. It sets some registers, sets some tables, but the hardware is the one which detects that and throws something back to you, right? Does that make sense? So you can't possibly let the exokernel be involved in every decision, because that way your machine will be slow as molasses, right? So you don't want to do that. You want to give as much control as possible. That means now you are changing the hardware in some interesting ways. I mean, they do mention it, that they're building this hardware kind of stuff, but essentially now their hardware would have to understand, not a whole lot, which is a good thing, right? But it has to understand this notion of a secure credentials. So I have to give you a credential which you cannot forge, and which the hardware should be able to check it, and you should be able to present it to the hardware every time you want it. And does that make sense? They don't say it out like that, but the whole, like in the middle, it's basically about how to address that issue, right? And yeah.
But the paper, like in the case of a page allocation, it says that the owner of a page can change its credentials.
Mm-hmm.
So when it does that, there must be some way for the OS to guard against that.
I think they change the credentials. I thought they changed the credentials and changed the way that it's accessed, not to change who accesses it. They change it from read write to read or what have you, where again we go back to the principles that we already know from undergrad OS, right? Which is, we don't try to prevent you from hurting yourself, right? So if you want to change a page from read only to read write and then modify something that you shouldn't be modifying, that's not something that we prevent, right? Yes, so you should be able to change the credentials to do something to the page that was allocated to you. But you cannot be given privileges to change the credentials of some other user, because the whole thing blows up, right? But the things have to happen in hardware, right? Or somewhere where it's faster, right? And if you can't do it faster, then you have to do something that you mentioned, which is basically assume that things are working fine, which will make a lot of people unhappy. I mean, and that will make me kind of scared. So that's the big issue. I think that's the one that this approach has to solve, right? At the conceptual level, it's very, very trivial, right? I mean, conceptual level, it says some users want all the power in the world, right? And for them, we'll give them all the power, because you only have 3 abstractions. We only have 1 abstraction, which is whatever resource you want, I'll give it to you as raw as possible, right? The only conclusion is I give you capability and you're not allowed. So the capability is secure enough that you can't modify somebody else's capability, and you can't abuse the system. So within the whatever I give you can do whatever you want with it, right? So if I give you a CPU, I don't care what you do with it. If I give you a disk block, I don't care what you do with it. But all I give you is this capability, and you can do whatever the hardware would let you do, right? That's the only thing we do. And so for people who really want the power, they have all the power. For people who don't want any power, they can just go out and buy these libraries from somebody else. So we solve both of them are happy, right? For most of the users, they don't particularly care, and they can go buy their POSIX from somebody else. So this app user can move their code from here to here. They haven't proved it because it just takes too much time, but there's no reason why this can't work, right? So you as application user, a hello world program can work on exokernel just easily as it will on a regular system, right? But for users who really want to do this stuff, they can have all this power, right? But with all the power, we still have to make sure that the resource allocation happens in a secure fashion. That means I have to be skeptical. The exokernel has to be skeptical of what these users are doing in terms of accessing resources that they don't have control to, right? I don't care what you do with the resources you have, but I care you try to do something else. And if I get in the way of everything, then things slow down. If I want to get out of the way, right? For this, it's sort of, it's one of the easy things, right? But then some of the other things, it gets kind of weird. For the network thing, that's why they say you need to move a code into it. And some of you mentioned we're not too happy with moving code into the kernel, right? So here you're kind of sending your code into the kernel, which does the check sort of for you, right? So you have to send this piece of code which will check whatever the network packet coming through to make sure it's for you or not, right? And as you pointed out, the idea of writing code which can be checked and all those things makes a lot of people unhappy, right? Do you like the idea of sending some code inside which will check my credentials, right? So I have get credentials, I send a code in to check my credentials, yeah.
Well, I guess my question about that whole process was, why wouldn't you just write a handler that says, well, I want to, and just take everything off the line, and then you could take packets that were supposed to go to somebody else?
Mm-hmm. That's an excellent question, right? Why won't you?
And I couldn't imagine why it would be a good thing for the operating system to let processes co-opt all the packets on the wire so easily.
I think that's an excellent question, and that's what I was trying to come up with this example here, right? So in here, I cannot do that, right? Because I don't have any control, right? But in here, right, I can prevent it by putting all the abstractions I had here, move it to here, which you don't want to do, right? But if you say I don't want that, then I think you run into the problem that you just mentioned, right? And they say, well, you can have proof checking code, you check the code, proof, and all those things to make sure that whatever you send into the kernel is doing what you're supposed to do. So essentially, you're moving the complexity of figuring out who should have what. If you have a hardware for pages and everything, the hardware has it, it's fine and dandy. For some of the things you apparently couldn't do the hardware stuff. If you couldn't do, then either the kernel can say, I will do the filtering and I will only give the packets destined to you, right? Which we don't like, because that means you're having mechanism inside. It has to figure out whether this packet is IPv4 or IPv6, or it has to do some processing. We don't want that. We want to be as far away from that as possible. So we have to ask you to identify what is your packet. And then we are supposed to check to make sure that you're doing what you said you're doing, right? You may be skeptical that this is not a good idea, right? But that is a problem we still face. I mean, that's a problem we still have, and that's a problem that we still see in a lot of other scenarios. But that's an actively researched topic. So how many of you read the paper on singularity, the other the recommended paper? That's a paper from Microsoft. So that's their next generation of operating system or something that they're working on, right? So if you look at that, so anyway, their idea is, you want to run it inside a browser, right? You want to run the operating system inside a browser or something. So you want to run it inside this one thing, where it provides you a little bit of abstraction. You have this notion of processes which run inside your browser, right? And you run into the same kind of issues. Like, how do you make sure that the code is, so you don't want it to be fully protected and basically run an operating system inside a browser. You want it to be these simple things where you want to prevent them from doing stuff. And if you read the stuff, one of the things they want to do is they'll have a language called SingStar, right? Sing hash, right? Like a C hash thing. So it's one of the things is it'll do proof checking, right? So hopefully when you write it in Sing hash, it'll prevent you from doing certain stuff. And that's some of the things that they're doing here too. So you'll write your filters in some language which could potentially be checked, right? And so that will prevent you from doing what exactly you mentioned, right?
Well, I guess my question is, how are they checked, right? Because who's to say that I really don't want all the packets? Maybe that should be valid. So, because if I was writing a packet sniffer, for the entire network, and I wanted to theoretically say, well, what's coming along the line, regardless of who it's for?
That's excellent. That's an excellent point. And so let me put it this way. Is that question fundamental to what they're trying to do? Can you solve it without, is that fundamental to what they're trying to do?
Well,
is that a trade-off that you have to take, right? Can I possibly give you all the control you want?
I guess not, but it just seems interesting that they're trying to say, well, we're not going to do anything, but we're going to do some things, even though that prevents you from actually doing what you want to do. You know what I mean? Because there are some cases where you might actually want all this power. And yes, I can see in the general case it would be bad to allow more bosses to do it.
So how many of you felt that if you read the paper, sometimes they do this dance, right? They kind of say, we want to do this, but then we run into this problem, and this can be solved using this, right? So we want to be able to do the secure allocation, but then it's extremely awful because everything has to be slowed down because I have to check all this thing. So what I'm going to do is I'm going to push the complexity to this undefined programming language, which can be built, which will control exactly what you want to do, right? Which, from their argument perspective, shifts their complexity to somebody else, right? And I think next slide I'm going to bring it up, which is all of this brings up to the issue of who is we and who is they and who's trying to do all this stuff, right? So I can write a paper and say what I showed was very hard. I didn't lock the program. What I'm trying to do is very hard, but basically I'm going to solve it by expecting this other people who will solve the problem, so I'm going to move, right? You as application user don't care who this people is. I mean, you want the whole package. You want it by from Microsoft or whatever. And it's an extremely hard problem. I don't know what the and that's the challenge in all the system, right? You get the benefits, but you have to kind of do this stuff. And so they have to do this sort of, you read this thing, to me, when I read the whole paper, it sort of comes across as, yeah, it's good, but then there's this cost, but then you kind of solve it by kind of doing this stuff. Yes, it's kind of bad. It's kind of bad to do this stuff, right, for the pages. So we do that by having the hardware understand secure bindings. So now the hardware has to understand the secure bindings, which means that this hardware and the software are kind of mortally linked, right? So now you can't kind of change the way software does stuff because the hardware has to understand. So in the case of the page table and all those things, it only needs to know the virtual address and physical address. But here it has to know how to do this securely, how to give this credential which cannot be morphed, right? So if you ever want to modify this stuff, if somebody says, I want to create a new Exokernel where the way you create the secure credentials would have to be different, you can't because hardware has to go along with that, right? So there's all the price you have to pay for doing this stuff, right? And though it may look sort of confusing, there's like no end, this is an active stuff that people are trying to figure out what to do, right? You love the power, but you can't handle the consequences of the power, right? You can solve it very easily by taking away the power and abstracting stuff, and then you go back to the microkernel and you're trying to do this stuff. And so the next notion is the visible revocation, right? So what is the visible revocation, the idea of visible revocation? Yeah.
It's whether the library whose resources are getting revoked is told about whether it's getting revoked. So if it's visible, then the library sees sees that their resources are getting revoked. Or if it's invisible, the kernel just takes it away and they don't get notified. So
what's good about visible revocation? So the last one is abort protocol where you're not told, right? I mean so what's good about visible revocation?
It allows the library to react to the revocation in its own, to make its own decisions about what to do about that revocation, and so that it can, inform the program that something went wrong, or it just gets to decide for itself. It has all the power of what to do.
So what's bad about the visible revocation? So why do we need this abort revocation?
It has overhead associated with it, so it's not as fast, and you also can't guarantee that the library is going to give it up gracefully. If you're nice to it in the way that you take away the resources, and you can't guarantee that it's going to be nice to you back. So you have to have a way to just forcefully take it.
Yeah, I mean, they have to be nice, right? Because they have no power over you, right? I mean, the Exokernel can take it away, so you better be nice, right? Because, I mean, you're going to lose, because if you don't do this, next thing I'm going to do is use the stick, right? So I think one of the interesting aspects here is there are three kinds of things which can happen, right? One is you really want to know when something is being taken away from you so you can do the right thing, which is the reason why we built this whole thing. I want to know when a page is being taken away from you. So not only do I shrink my program, but I also know which page was taken away so I can change my scheduling algorithm and all those nice stuff, right? Then there's this malicious users who don't want to give it away. So I say, give me a page, and then they say, no, I'm not going to give it to you. Then you use the stick and then take it away, right? So that's the thing. This class in the middle, right, where they're not able to react fast enough. They're not able to do stuff well enough. They're not able to do. So the OS is telling it something. I want to take a page away, right? And the program may say, no, don't take the page away from me because if you take the page away from me, I need like at least 4 pages for me to do stuff, right? I need at least 4 pages. Remember, we should have read about this from your undergrad OS, right? The thrashing and all those things, right? So it knows that it needs 20 pages, right? And you want to take away some page from me. So it's not being malicious, right? It just knows that it wants 20 pages for it to do. Otherwise, it's going to thrash it. It's not worth doing the stuff, right? Is that a problem? Do you ever run into that case? I mean, all the 3 cases, clearly we know how to solve the first one because this mechanism is designed for that. Clearly, we know how to do the malicious user, which is the abort protocol. What about the users who know what they're doing? How can they interact with the operating system? They do address this issue, right? Remember, one of the things that they use this 4 pages, right? They said some of the things you need 4 pages, so we decide to give each process at least 4. I believe it's 4 or 5, right? So some small number, right? So this magical number now comes in because it's no longer pure because you know that that's at least the least you can give the stuff, right? So you have this notion, right? Is that a common case, and how do you deal with that sort of issue? Is that a trivial thing, and how do they address those issues?
Didn't they put a kind of timer on it? Like you could only, if a library didn't react right away, then it gave it some amount of time to keep going, and then after that amount of time.
I thought they didn't. They took it out because they said the time didn't quite work with the applications which didn't understand the real-time nature of the stuff, right? I thought they tried it but didn't work because applications don't know how to react fast enough, kind of thing, right? Are you satisfied with what they did at that point? I mean, obviously they do something and then they go to the abort protocol, right? But for that, things in the middle, how would you deal with them, or are you satisfied with this, with what's going on? For applications which really want to push back.
Well, didn't they have the ability to like kind of suspend the process and put it all into like some kind of
But yeah.
suspended state, and then when resources were available again, the kernel was supposed to bring it back to life?
Mm-hmm.
So that's kind of what you would do in that case. You would kind of tell the exokernel, save me to some persistent storage or whatever, and then whenever you're ready to give me what I need to kind of bring it back.
So would that be enough for all the cases you can think of?
Probably not, but that's one way.
Mm-hmm.
Another way is since the process knows that it doesn't have enough resources, it can just kind of say, well, if I don't have enough resources, then until I get enough resources, keep requesting resources.
Mm-hmm.
So it could get around it that way.
Mm-hmm.
But in any event, I mean, the problem is that if it really needs to run right now, then it's kind of
Yeah, so I think the problem is there are mechanisms you can think of, like, freeze me somewhere, give me 4 pages, and all those things. So you're adding these mechanisms in. You see the mechanisms creep back in, right? So first we start off by saying only policies, no mechanisms. Policies are all up there. Mechanisms should be all in the library space. Now you're letting some of the mechanisms kind of creep in because some of these issues are really hard, right? And you have to avoid that, because if you leave doing mechanisms, we are going back to the microkernel world, right? do you see the challenge here, right? So even though it's like a three simple things, for some cases it works really well, and for some cases it does not work all that well, because to solve that is to go back to the traditional way. I mean, the way to solve that is to move a lot of mechanisms and give you options and all those things, and then the exokernel is kind of becoming bigger. It's making all the mechanisms for you. Now it's going to support this notion of a freezing a process and getting it back kind of thing, which you don't really want to, because that sounds kind of weird, because right. So that's the tension here. I mean, it's kind of hard to figure out where things should go, all those things, right? So things to think of, right? So what, in terms of trade-off, what is the benefits and what's the overhead, right? And then of course they show that the performance was fantastic, right? So what do you think of the performance that they achieved for the stuff they did, right? I'll show you a little bit of slides and think more deeply into what does performance mean, right? So it's simple. I think it's simple if you stay simple, but then when you go into real case and make things more complicated, it's a challenging problem to solve, right? So how does it compare to something like a DOS, right? Like DOS, I mentioned, lets you do whatever it wants. So essentially you get the whole kernel, right? So essentially you get rid of this whole exokernel, and the POSIX library essentially implements the whole thing, right? Why is it different from that?
Because you're the only thing running.
Yeah, so now you want two of these things, right? So how often do you want two things to be running on the same system?
Most of the time.
Most of the time? So, okay, I'm not saying how often do you want to run two processes. I'm saying how often do you want to run two different stuff, right? So if you have all POSIX people, right? I mean, here they have to have POSIX, then they have shared library and all those things. But essentially, I'm saying, what is wrong with monolithic kernel for most users? So we're trying to solve two problems, right? One is database users should be able to write their own kernel. We solved it, the exokernel. So why do we want database people and game developers on the same machine at the same time? Which is what you get by having this, right? If all you have is a bunch of people who want to bunch of games running on the same machine, you can build a game hardware, game console, game whatever, right? So yes, compared to DOS, it's different because it can let two people run. But the question is, why would you want to do that? Or would you want to do that? Is it important to you, right? Personally, I don't know what the answer is, because they don't discuss that. It's assumed that you want to be able to configure two different things, but I don't think it's that important to run both of them on the same machine. Or I haven't seen the case for why you want to run two different stuff on the same machine, right?
I can see where you would want sometimes to have a very specific implementation, and then other times where you'd want a more general implementation. Like, for instance, if you have a game machine, presumably you're not just playing games on it, you're also doing, browsing the internet and doing other things where performance is nice, but you can kind of wait the extra tenth of a second for the frame to load.
Mm-hmm.
So you can kind of, if you want to look at it that way, I don't know if you necessarily want to have a database and a normal machine, like a home PC on the same kernel, but
yeah. So
or like movies. You said movies as well, so you might want to watch a movie and then play a game and then browse the internet. Mm-hmm. All three of which you could theoretically load in the libraries to do, to perform whatever you want to do.
Mm-hmm.
Yeah, I was going to say, if you have multiple applications like that, aren't you essentially going under microkernel? As you're adding functionality, presumably your file system for your internet browser, you need special file system for the database engine, so you just kind of...
Oh, that's a good point, right? So if you add more of those, then microkernel is also in the mix, right? So how does that play into? So some of you may, anyone working in embedded systems, in architecture kind of stuff, right? So one of the things that embedded systems do is they do this similar kind of stuff, right? So I think betas and all those things. Essentially, this is the kind of stuff that runs in your car. So when you're running something in your car which is controlled